Hello, and thank you for coming in. And my name is Gareth Thomas. I'm the Managing Director of Metal Innovations. Started my working career in the mining industry back in 1980s, about 81, I think it was. Since then, we've been plodding along. We've been involved in the miners' strike. After that, I started my own business in 91 and moved on from there. So I'll just talk you through these slides, and we'll go one by one. You can get me on the email address attached if you wish to contact me. Metal Innovations is a company that I started in 2004 with a couple of £1,000, built up machines from that. What do? We specialize in the design of bespoke equipment, whether that be in coal, whether that be in canals, underwater, and who for? Well, anybody who's got the money to pay. Where did we come from? After years of research and development, and after the miners' strike, I worked on small machines, predominantly for small mines. This is the alligator, the up to the top of the boat on the tank there. Here is 24 inches in old money, or 600 millimeters. This machine has a cutting range of 14 foot wide and 7.5 feet high. To pay for this, we got involved with the with general engineering and fabrication. This is the moving walls in Cardiff International Arena. They were the first hydraulic walls in the world that we are aware of. And we did it for Brent Walker. These walls were opened in 1993 by Her Majesty the Queen. We went on from that, and we designed and built river dredges, waste sorting stations for L'Oreal, Revlon, Sony, as well as paper shredders and barrel crushers. And then late 90s, I should say, took the little alligator and we did some tests with it. Here in the UK, the mines are shutting down at an astonishing rate. So what I did was I bought a small mine, and then I started testing the machines in mines. At that time, we had very little money, if any. So this is the alligator here, as you can see, and this was the prototype of our 4500 R1. And that machine we built on the surface of the mine. Here to test the ground, we had in the seams here, this is the Money This Line seam, and this is a Black Barn mine in East Wales, near Blaenavon and Pontypool. What we were trying to do here is to see how long the ground would actually stand. So we built this little machine, was remotely powered, could cut forward around about 7 meters at about 18 inches, or say 500 mil wide, so that we could take a strip forward 7 meters, bring it back, set it up then like a little face machine, a shearer, and as it was going in, then set conventional supports. Here then we moved into our first version of the CM 1500 machine. This machine is 1 meter wide, and on the left, the picture on the left-hand side, the machine, and that is me there on the machine, we're cutting up 1 in 3 to the rise. The 2 seams, we had the bottom in the Money This Line. We had the bottom seam, which is around about 900 millimeters section. We had around about 1.2 meters of dirt. And then in the top coal, the old timers had mainly mined it around 1825. And it's 5 foot of coal, but there were significant pillars of coal left there that we could chase. So we went into bespoke design and engineering. We evolved into a full computer-aided design studio. The equipment was aimed at that time at small seam mining. And we worked specifically to customers' requirements. They were versatile, simple, and effective. From the original R1 or 4500, we did achieve some funding from Smart Cymru, which is government funded here, and we built the first of the true 4500s, as you can see there. So this machine was again aimed at a small road header with a reach of, it has a reach of 4.5 meters high. The arm could go through virtually 180 degrees. The material is moved through the center of the machine via a 2-inch flight bar for ease of clearance. So we were looking at stepping up from a small mine where they would traditionally use explosives or an air pick and a shovel. So this was our attempt to step up from there. So today this is the same machine, but it's the Mark IV, the same reach, material through it, up to 3 ton a minute, depending on the material that the machine is cutting. So here, this is Aberpergon mine, and what we were doing is demonstrating that it is a modular system, simple to assembly, and with ease of maintenance. Installation normally within 1 working shift, up to 2 kilometers inside the mine. Delivery on a truck or in a shipping container. Production within 1 day, more or less flat pack system with quick release couplings. Very little, if any, spanners actually required for installation. So we moved on. We perfected the 4500. That was the intention was to use that as a small road header for accessing small coal seams of about 800 millimeter section. So we went from the 1500 with a single cutter on, and we put a double drum cutter on. In the coals in East Wales, the advance rate was up to 1.5 meters a minute. So when we put the machine into the harder coals in West Wales, the anthracites, the 1500 bounced off, literally bounced off the cone. So we came up then we went back to the drawing board, we redesigned, and we came up with a CM 1700, which is a much heavier machine, more powerful, that you can see on the right-hand side. So here is a 1700 in operation. It's a 0.85 meter seam, as you can see there. You can see Mike in the left-hand top drawing, or picture, I should say, and you can see the continuous miner behind Mike there, to give you an idea of scale. So we would go there and go out as much as 300 meters in that section. On the bottom right, you can see the bridge belt system overlapping. So it'll allow us about 7 meters advance before changing the cartridge. To change a cartridge, it'd take around about 30 minutes. So here is the machine, and this is on Nantir mine in West Wales, UK. Even though we own the mine, the machine was delivered to the surface, and the usual tests conducted by the engineers to make sure that the machine was suitable for purpose. So, okay, we designed the machines. We asked conveyor manufacturers to manufacture conveyors to suit the scale of operation that we were intending to do. Unfortunately, we could not get conveyor companies to work with us. So we then designed our own conveyor systems. These double drum drives are 600 millimeters high and can pull 400 meters. So we designed the bridge belts. We designed all the intermediate conveyor sections, built everything ourselves, all the drive heads, and we had the gears manufactured. So now we had compact conveyor drives. We patented some line pans back in the 90s, and they were copied by PSC conveyors. We had transfer points, surge bunkers, shuttle cars, and power packs. All this we had to design, develop, test, and commission in order to give our machinery the best possible chance to shine. So we had a request from an American company to go to Colombia, South America, to look at some of the difficult mining conditions there and come up with some mining plans, and then to design equipment to work in the, well, near vertical seams there. So you can see here, so what we experienced there was anything from horizontal to vertical, and we needed to look at how we would work machines in those conditions. So this is what we did. We designed a flat pack system. So all this, so it's a full mining system designed to mine in vertical seams. It's a flat pack system that can be delivered in shipping containers anywhere in the world. A low-cost modular mining system. This system there was capable of near 500,000 tons a year. The machine, that's me standing there, the machine I'm standing under there is 560 millimeters wide, total width, and can run on its side. It can operate vertical and near to horizontal. And in the near picture here, these are our CM 4500 machines. So we call these CM 4500/560s, as they were 560 mil wide. When we were in Colombia, we looked at a lot of the operations there, and I went underground in maybe 30 to 90 mines, I can't remember. Looked at the mine conditions, looked at the operations with the artisanal miners, and how they might be brought into working with the government or with a much larger mining company. So what we did, we came up with this little machine, which is 800 millimeters wide, 1.9 tons, can carry a cutting head, rock breaker, drilling rig, so you can bore fire, or we can cut the material out, or we can use a rock breaker. Conveyor through the middle, the same, and this little machine can move about 40 cube an hour. Here we worked with, as part of a project funded by Horizon 2020 called the Impact Project. And our part in that project was to design the actual extraction machine for working in rock, which we'd not previously done, because we were in coal. So we used the same principle as our 4500, and we called it the CM 4500 MIDI. This machine is 1.25 meters wide, about 6 tons, height of 2.3, the length of 5.4, 5.5 meters, 55 kilowatt, electric over hydraulic. We designed the cutting heads, the whole machine, and manufactured everything here in our factory near Cardiff, in South Wales. So what we wanted to do then was to look at, once we got this machine, and we cut the ore, and this was in a lead mine in Bosnia. We cut up to a rate of 15 tons an hour, and we're able to select high-grade material for extraction. So here we went, we took the same machine, we modified it, we put different cutting heads on it, and we took it into London, and this is actually Chelsea Embankment in London. And this machine drove this tunnel and came back about 2 weeks ago, actually. So you can see the diameter of the tunnel. This machine can cut out a meter in about a little over an hour. So in the meantime, we were asked by a company working with Welsh Water, or the local water authority here, could we come up with a concept to save them pumping reservoirs out when they needed to carry out maintenance on the outward side of the reservoir. So this machine was designed to run underwater at a depth of 30 meters and 160 meters out, down a tunnel to block the outlets of the reservoir so that the maintenance engineers could change the valves on the outgoing side of the reservoir going into the water treatment plant without the need to drain the reservoir. So as you can see here, you can see Chris in the background there, and all this was done with a little 250cc Honda petrol engine. Again, we built the whole power pack, control systems, the whole machine. So later, the same company came back and asked for a machine half the size. So we set to work, and then we designed this. Is called the Valliant, much smaller machine, half the weight. All right, it hasn't got such a payload, but it carries the camera, and this went again down the reservoir into a much smaller tunnel, cleaned it out, then we fitted pumps to it, and it went down and sucked the silt out and pumped and cleared the outlets. So this is, you know, the type of thing that we do. We've done it since the 90s, really. So what do we do? You know, we evaluation of a project. We, as engineers, we review with the client and agree the objectives, and try to come to an agreement on costs. Generally speaking, the customer knows what they want to do. They just don't know how to achieve that. So we work with them to try and try to do that. So we carry out a site visit, we conduct asset, we look at the access, we look at the materials, we look for material hardness, characteristics, including orientation, using films, photographs, and basic plans. Preparation by an engineer of a document outlining how the objectives might be achieved is carried out by MI. The team at MI meets to evaluate and review the project and data on the report. Once agreed that the project can be delivered in budget and on time, basic 3D models of what we are going to do are constructed. This is discussed with the customer before the design stage commences. Progress is normally conducted in a phased way so that the customer can decide whether they can afford or want to continue, and the same for us as MI. So we do this all with an in-house team. So these are some of the machines, not all of the machines. As I said, we've been on this road since the early 90s, and this is a small selection of what we actually do now. So if there's any questions.